Electromagnetism, electromagnetism, is the source of all our power as X-ray techs. Oersted discovered that a wire carrying a current produces a magnetic field, and that magnetic field forms concentric circles around the wire. Then someone thought, well, what happens if we run a current through a coiled wire? Interestingly enough, we get a magnetic field lines that look like this. And there are a few unique properties about this type of magnetic field. The first interesting property is that if you reverse the current, the polarity switches. The next interesting property is that as you increase the amount of loops in the coil, you increase the intensity of the magnetic field. Also, if you place a ferromagnetic material, such as this iron rod, inside the coil, it too increases the intensity of the magnetic field. Finally, the strength of the magnetic field is also determined by the current. So, if we swapped out this small battery with its small current to this large battery with its large current, it will also increase the intensity of the magnetic field. Then this dude Faraday came along, and he had a brilliant hypothesis. He thought, if an electrical current can induce a magnetic field, can a magnetic field induce a current? And the answer is yes. He discovered that you can create voltage by changing the magnetic field. And this is called induction. Magneto would tell you, think of induction or inductance as a mutant power. Electromagnetic inductance uses magnetic fields to produce voltage, or in a closed circuit, a current. There are two variations of this mutant power, self-induction and mutual induction. As the switch is closed and current flows through the circuit, the electromagnetic field in the inductor forms and expands. The magnetic field created by this current increases voltage in the same circuit. Therefore, the voltage is self-induced. When we open the switch, the light bulb does not immediately turn off. It gradually dims as the electromagnetic field retracts. We can visualize the gradual increase in current as the electromagnetic field in the inductor forms and expands. When two or more coils are physically close and magnetically linked together by a common magnetic field, they are said to have mutual inductance. Mutual inductance is the basic operating principle of motors, generators, and transformers used in our X-ray machines. Mutual induction requires an alternating current, and we know that when you reverse the current, polarity switches. We learned earlier that as you increase the amount of loops in the coil, you increase the intensity of the magnetic field, and an increase in magnetic field changes the intensity of voltage and current. This example here is a step-up transformer. There is a higher voltage on the right set of coils than on the left because of the increase in the amount of loops. We said earlier that mutual inductance is the basic operating principle of motors, generators, and transformers used in our X-ray machines. An induction motor is used to spin the rotor. A generator is used to power our X-ray machines. That big box you see in every X-ray room, well, that's the generator. And within that generator are transformers that set our technique, produce the appropriate mass, and convert 220 volts to 125,000 volts. An electric motor is a device that converts electric energy into mechanical energy, such as motion. Here, Current running through the coil of wire causes the coil of wire to become electromagnetic through magnetic induction. The coil of wire's magnetic field interacts with another magnetic field, causing it to spin. An electric generator is the opposite of a motor. An electric generator converts mechanical energy, such as motion, into electric energy, producing an induced voltage and current. For an electric generator, a coil of wire needs to rotate in a magnetic field produced by a magnet. The changing magnetic field as the coil of wire rotates forces electrons through the coil of wire, inducing current and voltage. Here's another example of a generator. As the magnet is pushed and pulled through this coil of wire, it forces electrons through the coil of wire, inducing a current and voltage. A transformer changes the intensity of voltage and current. There are many variations of a transformer. For example, this is a step-up transformer, which has a ferromagnetic core. We'd call this a closed-core step-up transformer. We use these exact types of transformers in our generators to convert 220 volts to 125,000 volts. This is a closed-core step-down transformer. We use this type of transformer when producing MA. This is an auto transformer. We use this to select the appropriate kV and MA values. And finally, this is a shell type transformer. We do not have these in our radiographic equipment. We can calculate how much voltage will be gained in a transformer. The equation is voltage on the primary side divided by voltage on the secondary side, which equals the number of turns on the primary side divided by the number of turns on the secondary side. The primary side will always be the side that has the source of electrons. We can calculate how much current will change in a transformer. The equation is number of turns on the primary side divided by number of turns on the secondary side, which equals current on the secondary side divided by current on the primary side. Combined, the equations look like this.